of lectures. Our problem was to calculate the function of W of a background Maxwell field A, which was defined by the sum of two terms. One term is the classical Maxwell action, and the second term is a constant times logarithm of determinant of the Dirac operator in the background. There is also master in the background of this vector potential A. And we showed that there is nothing here to calculate. This one we expanded to the power series of A, and our objective was to calculate up to second order term. And we wrote the answer eventually as in the form of, we used the Fourier transform, went to the Fourier space, and the answer was written in this compact form. This is just the classical part. You will see it because it has a factor of 1 over E0 squared in it, which originates from there. And the coefficient, I should put this here. This is 1/2. And the contribution for coming from the loop part, we called it pi mu nu k. And the big portion of our time in the last lecture was to evaluate this pi mu nu k. Let me make a general comment about this pi. We saw that it's ultraviolet divergent, and we used dimension regularization to calculate. But what do you expect it to be on general grounds, on the basis of Lorentz invariance only? Well, this is a function of k, and there are two tensors. Grazie. There's no shock.
I give you some.
Thanks. There are only two possibilities, only two tensors at our disposal. One is k mu, the other is eta. And it should be a Lorentz tensor of second rank. So, on general grounds, therefore, it should be a combination of these two tensors. Okay? Whatever combination it is, you can always bring it to this form. You can always bring it to this form. This is the same tensor which appears here if you factor out k squared. I wrote it in that form because it's more common, because it's a projection in that way. Later on we will call this p mu t, and we'll discuss it more. It's t means transverse, and this one we will call p mu nu L. L means longitudinal. And the properties of these tensors is that they are projectors. The projector normally squares to give itself, so this one squares to give with a -1 in front of it. But that doesn't matter for what you want to do. The important thing is that they are orthogonal. So if you hit this with that, k mu acting on this, you see that k mu acting on P mu nu transverse simply gives you minus k nu plus k squared divided k nu divided by k squared. It is minus k nu plus k nu, and that's 0. So this tensor is orthogonal to this tensor. Okay? Of course, you can take this term always combine with that and write as eta mu nu plus some other function times k mu k nu. But this is more convenient way of writing it. Our calculation showed that this function is 0 in dimension regularization. It took a long time, actually, in the history of development of quantum electrodynamics to find the regularization which produced only this term and not the D. Okay? This was eventually solved the problem by Pauli and Villars. Villars regularization also will produce this structure with D equal to 0. It's a perfectly good regularization scheme for one-loop calculations like the one that we are doing. But it's not very convenient if you go to higher loops. Dimension regularization has this advantage that it's rather straightforward. Conceptually, it's a little bit perhaps not very clear, and also it is not directly applicable to chiral gauge theories, for example, because the chirality is a notion which is defined only in even dimensional spacetimes. You do not have chirality in odd dimensional spacetime. Here we are making the spacetime dimension a complex number. Therefore, the notion of chirality is not applicable. So, however, for most applications, it's perfect, especially, I don't know, in non-abelian gauge theories. So, this is one example where the usefulness of this regularization scheme is shown by showing that this longitudinal term does not appear. Okay? We will have more to say about this term and this structure. You can obtain quite general results up to all orders from the fact that you can write that pi in this way. We calculate pi, remember, eventually, the thing that we are calculating here is in terms of graph, it's this graph with two external A lines. For us, the external A lines are classical Maxwell's field. Okay? But when we look at the exact propagator, photon propagator, this will be just the first quantum loop which will contribute to the three-level propagator. We will discuss this later on in great detail. If you have quantized A field, of course, there will be other contributions like this. A will start propagating also in the loops, and there will be infinite number of more higher loop graphs. Okay. In our calculation, we do not see this because A is not quantized, and we saw that integrating over the terminals produces just this term, which produces graphs with arbitrary number of external A lines attached to it, but no internal A line. It's only one loop graph. This is a two loop graph. Okay? So even if you go as general as assume that you have written all the terms, you can say quite a bit about the structure of this function simply from the fact that it can be written as the sum of two terms like this. Okay, so that was a remark which I thought is useful at this point to make, and later on, hopefully, we will have more time to discuss it. The point to which we arrived was an explicit form, final form for this phi mu nu, which, so pi mu nu, as I just mentioned, is proportional to this tensor, k mu times k squared times the tensor, times two terms. The first term I'm going to call pi singular and then pi finite. Pi singular is in fact a constant. It is it's just that. This coefficient, I think in the previous, in the last lecture, I had not copied this correctly, this coefficient. It will not matter for what we are doing, but it's good to have it correctly in the notes. So in correcting these notes, I realized that there was a typo in there. But this, the finite part, is the part that we are going to elaborate on further today. Is in fact, I have written it I think correctly last time on the blackboard. The integration is over the final parameter from 0 to 1. And I think today I have written it as the minus sign in front. Okay. The way we proceeded was to say that this constant piece multiplying that tensor has precisely the same structure as the classical part. Therefore, it should be combined with this constant piece. So this tensor is going to multiply a constant number, which is the sum of this term and this term. And then the rest should be written. So using that, then, so defining 1 over E0 squared minus 1 over 12 pi squared times 2 over delta minus gamma, calling it as this a redefinition of the parameters, if you like, 1 over E squared. And the whole thing we wrote as WA. I think I also gave a name to this and called it, this part I think we called pi of k squared. And W is written as d4k over 2 pi to the power 4 with a mu minus k. So that's 1 over E squared times, not enough space here. So I go to the second line, 1 over E squared times minus k squared mu minus k mu k nu plus pi of k squared times nu k.
Shouldn't that be a plus?
What?
In the factor minus k squared it will be a plus.
Where should be a plus? This one, yes, this one. And tensor should multiply everything. So I didn't write it correctly. I think I should open it. So I should open square bracket here and write 1 plus k squared times. Okay. So this 1 times this term is that term in which we have replaced 1 over E0 by 1 over E and absorbed this division piece. The rest is the finite part. Okay? This is the expression we would like to study now. Questions?
Can the singular part depend on the momentum?
Sorry?
The singular part, can it depend on the momentum? Because you wrote that it depends on the momentum, but there's no explicit momentum dependence on it.
Well, it's a constant function. It's a constant function.
You can write k power 0.
I could have. Okay, the k dependence of the singular piece is just this transverse tensor. Okay. Yes.
I think that the question was that can a momentum-dependent part could be could be singular.
This is the hallmark of the renormalizable theories. That if there is a singularity, it is polynomial in the momentum. So the singular part is not just this. In reality, the singular part is this part times that. Okay, the whole thing. But the structure of the polynomial is such that if you sandwich between two A's, it will produce precisely the same term as classical Maxwell's term with a different coefficient. That's the reason why we could absorb the singular part in redefinition of 1 over E0. If it didn't have that structure, you couldn't do that. If there was another function of k here, if it was different from this, you couldn't absorb it there. Or if you use the regularization scheme in which there was a mass squared here times eta mu nu, then there is nothing in the classical Maxwell's action to absorb it. So you would get a mass term from the photon. Okay? Other questions?
Actually, can you see that this pi mu should have this form just by applying modulatorly?
No, you don't need that. This is much more elementary than that.
Okay.
The modulator will give you other information, but not this one. This is just a Lorentz property of the left hand side. It's a second rank symmetric tensor.
But why does it explain that we should have a minus sign in front of eta mu?
Well, the minus sign, right. I mean, it's dictated by the. There are various ways you can see that. The minus sign has nothing to do with model identity, because if you could absorb this with that and call it different function. In fact, you could even absorb this minus sign there. This, I didn't tell you what this pi is.
I'm talking about the relative sign of eta mu.
No, you could take this to you could write as eta mu nu times pi of k squared plus k mu k nu divided by k squared, not pi. Call this d1 and call this d2.
Okay.
If you know precisely what the order identity is, then you can use it to bring it to some form. But for this, you don't need the order identity. So you just decompose into two orthogonal directions. This tensor is orthogonal to that. If you don't have that minus there, it will not be orthogonal.
I was saying that we can see that the d should be 0 by identity. The upper d.
This one?
Yeah.
No, the order it doesn't tell you that it's 0.
Because if we
If you apply a different, no, the borderline does not tell you that D is 0. The borderline eventually will tell you that D does not take corrections from higher order loops.
oh, okay.
Not 0. In fact, it's not 0. Even at the 3 level, it's not 0. You can choose, if you see this, you can choose the so-called, for example, covariant gauges. There will be a psi-dependent term here, and this is 0. Other questions? I should keep that this is the definition of pi. We will use this part. I can erase. Okay, so what are we going to do with this W now that we have calculated it? W is a functional of classical Maxwell field A. You will do with W whatever you do with the classical action. What you do with classical action. If you have classical action, you derive equations of motion and solve it. So, therefore, we are going to study one quantum loop corrected Maxwell's equations and look at its solutions. Okay? This is the physics comes from there. And generally, when you want to solve Maxwell's equations, you couple your field to a source, to a current. So what you want to do, couple a mu to a current J mu. And I'm going to do it in the momentum space. So all we need to do is to add a term like J mu tilde minus K A mu K. Okay? So this is a source, external source, coupled to the Maxwell's field. And we assume that's given. Somebody has given this source to us. We will see that it has to satisfy the conservation law simply because of the structure of the action. So the classical equations of motion for the A in the Fourier space, right, minus A, in the Fourier space becomes, actually let me rescale, I should have done it before coupling to the source. So before coupling to the source, I will rescale A. The only effect that it will have,
It's up there.
it's up there. If you remove this, I put in fact it outside. Therefore, if I rescale it, it will go away. But then I've forgotten to put this e squared there. The way that I have written it, this pi is not an e squared. So this 1 over e squared will multiply this pi. Therefore, I should have put an e squared in front of it. It was a mistake the way that I wrote it. But if I rescale A by sending A to e times A, this overall 1 over e squared will cancel. So send A to e times A. There's 1A there, 1A there, 1A there. It will bring up A squared and it will cancel them. After I have done this rescaling, I couple the source there. So this source and this A is that rescaled A. Okay? You could have kept it also here, but it will be just inconvenience. I could always absorb in J and call it another source. So this is the action we are going to study and erase this one. If we have done that rescaling, that E will not be there. So these equations will give us, it's very easy to work out, it's a bilinear action. There is one term, 1A there, 1A there. The variation will produce two terms which will cancel that factor of 1/2. And the equation of motion will be minus K squared eta mu mu plus K mu K nu times 1 plus E squared pi of k squared times a tilde mu k equals to j tilde mu of k. You can put this sign minus so that when I take j to the other side, it will be plus. This equation, like Maxwell's equation, immediately tells you that the source should be conserved, because if you multiply by k, nu, k mu, this will be k mu. But this tensor is 0. If you multiply this by k, you get 0. So this telling you that for the equations to become consistent, the source should satisfy that relation, which in x space it means d mu j mu x equals to 0. It should be a conserved source. The way you solve these equations is, of course, if this operator here is a matrix, if it is invertible, then A would be given by the inverse of this matrix times the inverse of this expression times J. But this operator is not invertible. In fact, it has a 0 mode, and that's the reason why K acting on it gives you 0. K itself is 0 mode, for example. Okay? So how do we go around this problem in classical electrodynamics? We impose the gauge condition. So let's impose the gauge condition. You can always choose your gauge such that A satisfies some subsidiary condition, and we will choose it to be this. This is the analog of d mu, a mu. This is the Fourier space version of that condition. And this term will give you 0, and the leftover term, this term k times this k nu times a nu will give you 0, and then the rest can easily be inverted. What's left over? So, and the inverse is written quite simply. Therefore, the solution from here, subject to this condition, is that a tilde mu k equals to minus j mu k divided by 1 plus e squared pi of k squared. In the notes, by the way, I have put this e squared, this coupling constant squared here. But the end result, of course, is the same. Now, you can go back to the position space, if you like, and that's the solution. If the source is given, if you know what this vector is, you know what pi of k squared is, given here. Therefore, this is the one loop corrected solution to Maxwell's equation. We would like to study this equation in one important particular case. The important particular case is the case where the source represents a point localized charge. In classical theory, if you have a source which is just a point localized charge, what do you obtain? Coulomb potential. So this will be a correction to the Coulomb potential. You will see the effect of vacuum fluctuations on the Coulomb law, how the Coulomb law is modified. You can imagine that this should be an important thing, because Coulomb law is a very well-known, experimentally and classically very well-known law. So therefore, we will see what's the effect of quantum mechanics on the Coulomb law.
You obtain W by having a Lagrangian where the electromagnetic field was interacting with the fermion field, and then you integrated over the fermions. But so does that integration takes away the interaction, because you are now having another interaction in that?
This is an external source. We have to separate the two things. This is the effect of vacuum fluctuations of electron-positron creation. This is not that. This could be a classical electric source. For example, this could be the source of the case that we want to study, point particle source. It could be the source of the charge of the nucleus of an atom. The nucleus of an atom creates an electric field.
That's just a background field.
That's just background. See, we are not taking the dynamics of the proton and neutrons into account. We are just taking it as a charge distribution to produce a field. Interact with the electromagnetic field. Okay? So, Coulomb. In order to study this problem, we will take J0x to be a number which I am going to call Q, localized at the origin of the three-dimensional space, and the vector component of J equal to 0. That is what gives you the Coulomb potential in classical electrodynamics, that kind of source. This, if it is the source corresponding to a nucleon, that Q will be Z times the charge of a nucleon, where Z is the atomic number, the number of protons. And then we will plug it there and find the solution. So first of all, what I'm going to go slowly through this so that you see all the steps. Remember that this is the four-dimensional Fourier transform of J0x. If you substitute for the J0 what we have there, this becomes dx0 exponential minus I k0 x0 times d3x exponential of plus I vector x times vector k times delta 3x. There is also a constant q in front, which I am putting outside. So this gives you 1 by definition of the delta function. And what does this give you? It just gives you q times 2 pi times delta of k0. Okay? So we go back here and write our potential in the x space, if you like, to bring it to the form which is familiar to us from classical electrodynamics. So first of all, since the space components of J are 0, if the index mu here is 1, 2, 3, this will be 0, A will be 0. So we see that from Jx equal to 0, we conclude that the vector A is 0 in space components. The only thing which is non-zero is A0. And A0x, I've called this V of x, and hopefully I have not changed my mind later on, is of course the Fourier transform of J0 with a minus sign in front. For J0, we are going to substitute this. So this was our J0 tilde. We are going to substitute from there. That's minus Q times 2 pi times delta of K0 divided by 1 plus E squared pi K squared. You can immediately integrate over K0 because there is a delta function. So K0 will be set equal to 0 in this exponent, and 2 pi will cancel 2 pi. What will be left will be d3k over 2 pi cubed minus q from here times, I'm sorry, you did not stop me. I should have put a k squared here when I was inverting that equation. Because the equation was k squared times, you remember what the equation was. We were, after you use the gauge condition, the equation becomes minus k squared plus, you can use eta to lower the index. The equation was this. After you have imposed the gauge condition. Therefore, A will be this divided by this whole thing. Is the k squared. Now, the delta function is telling us that the time component of k is 0. Therefore, here I will have only the space component of k, and it will bring a minus sign because k squared is k0 squared minus space component squared. Plus e squared pi of, here also we should set this time component to 0, so it will be minus the space component power 2. And again, there is a bracket here, of course, 1 plus that. And then in the exponent here, we have minus I k dot x. Okay? It's just a substitution we are making. Clear?
So cancel that minus 2.
So this minus will cancel with this one, as it was correctly predicted. And let me just erase from there and erase from there. The reason I kept them was to show you that how they cancel each other. And this is a vector, of course. And pi is given here, in which this k squared should be replaced by minus space k squared. So the pi here is in the denominator. And when you expand this denominator, of course, there will be plenty of powers of, infinite powers of e squared, infinite terms with increasing powers of e squared. And we have done only one loop calculation up to the order of e squared. Therefore, if we want to restrict ourselves to one loop, we should just expand this and keep only the first order term in e squared. That's the order of our approximation. It means we should replace 1 over e squared pi of minus k squared by 1 minus e squared pi of minus k squared plus terms of e to the 4 and higher. Okay? We will do this. But before going any further, let me mention that despite the fact that we have done a one loop calculation, this expression has a meaning, even if you don't expand it like this. In fact, it is summing infinite number of graphs constructed from the single loop by just gluing them together as we did for the scalar field. If you did that, that's what you would get. So the way that we have written it is, in fact, it's not wrong. It's summing subset of graphs, if you keep it in that form. But for the time being, we will just go on up to the order of one loop. I will come back to it and make another important comment about it later on. So let's make the substitutions and see what we get. Finally, I can make use of this explicit expression for pi that I have been keeping on this corner of the blackboard in order not to write it again. We are going to make the substitution here and stare at the integrals that we get to see what they give us. So we are going to replace this 1 over 1 plus e2 by this expression. Therefore, v of x, which is the same as a0, is q d3k over 2 pi cubed exponential of I k delta x. There is a k squared here, which will multiply the 1 coming from there. Let me first write everything and then we write two equations. So the two equations is 1 minus e squared pi of k squared. That's our one loop approximation, where pi of k squared is given by this integral here. Now there is a 1 over k squared times 1, the first thing. So what is the Fourier transform of 1 over k squared? So that gives you Q, the Fourier transform of this, is 1 over 4 pi times 1 over mod x that you recognize as the Coulomb potential. Of course, our calculation should produce Coulomb potential, otherwise it shouldn't be correct. And then there's the extra term. The extra term has also a q in front of it. It is d3x divided by 2 pi squared. This minus sign comes from there. Oops, there's an error in the notes, but a minor error. K squared divided by this k squared, which was outside in front of everything, times exponential of ikx. In the notes, this term has been written twice, once there and once there. Obviously, in cutting and copying, I've forgotten to
pi to the 3, no? To pi to the cube.
Yes, thank you. And then there's, of course, also an e squared.
I have a question. If Q is of the order of E, it will be
This charge?
yes.
Yeah.
So it will be to the power of 3. Shouldn't be neglected in first one.
No, it's a background charge. You should keep that. You should keep it. In fact, eventually you will end up with this expression again. So
The exponential should be negative.
it doesn't matter. Negative or positive doesn't matter.
Yeah.
But here yeah, it should be negative, but it doesn't matter. This integrand is even with respect to k going to minus k. So you could change the sign. So the sum is, the result is the sum of two terms. One of them is the Coulomb term, and instead of writing absolute value of x, sometimes I write b of r, plus the second term, which comes from the quantum corrections. And of course, our main work is to understand the meaning and the implications of the second term. So let's substitute for pi and study the second term. The second term, let me write here. So if we make the substitution for pi from here, this is pi. So this should go there. There is a minus sign in front of pi here, which will combine with the other minus sign, and the total sign will be plus. Final sign of this expression is q e squared divided by 2 pi squared, that's this 2 pi. Then there is an integration over d3 k 2 pi cubed, and there is exponential of minus I k dot r divided by k squared. Then there is this integral 0 to 1 dx x1 minus x times log of etc. I'm going to give to that long expression a name. I'm going to write this as q, first of all, e squared divided by 2 pi squared. Remember the definition of the fine structure constant alpha, that's e squared divided by 4 pi. So put a 2 there and turn this into a 4 pi squared. Therefore, it becomes q times 2 alpha divided by pi. Then there is integral d3k 2 pi cubed times minus I k dot r divided by k squared times some function of k squared. This function of k squared is what is I have written here in an incomplete form, which now I am writing in its full glory. That's dx x times 1 minus x logarithm of 1 plus x times 1 minus x times vector k squared divided by m squared. This sign changed from a minus here to a plus there because this k squared is k0 squared minus k squared and k0 is 0 for us. Therefore, this minus sign changes that to a plus sign. This sign is important. I have not made any comment on that, but you should note that if k squared is negative, that means if k is space-like, this term will always be positive, and you will have a logarithm of a positive number. That's a real number. But k squared could be, k could be time-like. and k squared in that case is positive. If it is positive and large enough, this term can overtake 1, its negative can overtake 1, and the argument of logarithm becomes negative, and therefore it develops an imaginary part. Okay? How large should k squared be in order for this to be, the whole thing to be negative? That means in order for this to be bigger than 1 in absolute value. Well, it depends on how large, what's the maximum value of this, or how small k squared should be. I mean, what's the minimum value of k squared? It depends on what's the maximum value of this expression. X ranges between 0 and 1.
It's 1/4.
So its maximum value is 1/4. So k squared is starting from 1/4 times m squared. That means k squared equals to 4m squared. It will develop an imaginary part. What is 4m squared? It is 2m to the power 2. 2m is the sum of the masses of electron and positron. Okay? So that's the threshold for pair production. If k squared is space-like, then of course it's always positive and there's no problem. So therefore the imaginary part of this integral, this argument, hides important information. It has information about the pair production. If you remember, when we were calculating the loop integral, I introduced a function a squared of k squared. And in order to proceed, I say that we will assume that a squared is positive. Remember that? Then we forgot about that condition. And I promise that we will come back and discuss it. Now I'm mentioning it, I'm not discussing it, but I'm mentioning that if a squared that integration was not positive, it would not be positive. In fact, if k squared is time-like and equal or bigger than 4m squared. In that case, of course, it would be space-like. This argument will be negative and then the logarithm will develop an imaginary part. And that's a sort of chapter on itself. We have to discuss that chapter and understand what's its implication and details. But now we do not want to do that because it is not a problem now. The argument is obviously a positive argument of logarithm. Okay? So, then let's proceed with this. The next step is to do this integration, or to write this function in a form where we can manipulate it and obtain this correction to the potential, at least in various limits of small and large r's. To do this, we note that this is a total derivative. You can write this as x squared over 2 minus x cubed over 3, and do an integration by parts. So by an integration by parts, which will change the sign.
Why do you want to do that?
What?
Why do you want to evaluate the integral?
In fact, I do not even need to do that. Yeah? But I want to bring it to a standard form, which is called Uhling potential. That's the reason I'm doing this. But you don't need to do that. To extract the results that we want to extract, you can extract it in several different ways. This is the common way that you will see in some of the textbooks. So doing an integration by parts will give you this times the derivative of that term with respect to x. Actually, in all the ways that you want to evaluate this, I think you need to do this integration by parts. It's a technical point, but you have to write this in such a way that you can study with some ease what is the long distance and short distance behavior of that function. The way that we have written, it is not very obvious how to extract the behavior of the function for small values of r and large values of r. So we are going to rewrite in such a way that we can do it. Okay? So the derivative of the logarithm will give you the derivative of this divided by the argument of the logarithm. from here on, you can do various things. So what I'm going to explain to you now is one of the way of doing it, but by no means the only way of doing it. You see that even in the form, which looks complicated, but you see that if you take this I and substitute in here, this is what you want to do. Eventually you have to put that I in here and evaluate the K integration and then evaluate the X integration. This integration by parts produces a K squared here, and there's another K squared there. So the K squares will cancel each other. The only K squares which will survive will be in the denominator. And the integral is in standard form. So you can do the integration on K. Okay? But to make it a little bit nicer, I'm going to take one more step, a change of integration variable, and leave the rest to you to do. So there is a nice change of integration variable. Do I need this? No. I also do not need this. So we change the integration over x to a new variable. Change x to sigma by x equals to 1/2 times sigma plus 1. If x ranges from 0 to 1. When x is 0, sigma is -1. When x is 1, sigma is +1. So sigma will change between -1 and +1. And then this integral becomes if I haven't made a mistake with the coefficients, and I think I haven't as far as I could check it, is -1 +1 d sigma let me write the final thing. So if you take that 3 out, it seems to me that there is that's okay. So the way I'm going to write it is to multiply. Let me write in 2 steps, otherwise you will lose me completely. Okay. I wanted just to shorten it, but let me write one more step. You have to do a little bit calculation in order to get to this point. But it's not difficult to see where these various things come from. First of all, this number in front of n squared became 4. But this remained without 4. The reason is that 1 minus 2x, as you can see from here, is just sigma or minus sigma. 2x minus 1 is just minus sigma. So there's a minus sigma standing here. This product, x times x minus 1, is in fact 1/4 times 1 minus sigma squared. That's the origin of that 4. When you expand this, there will be a constant term when you rewrite in terms of sigma. There will be a constant term plus a term linear in sigma, so it will be 1 plus sigma cubed. But the integrand is, and there is one sigma outside coming from here. So it will be sigma plus sigma squared plus sigma to the power 4. The term proportional to sigma will integrate to 0 in the range, symmetric range of integration from -1 to +1. This is sigma squared, so it will give you just 0. Then only the even powers of sigma will remain. That's the reason why I have sigma squared and sigma to the power 4. Okay? Now I can write this integration from 0 to 1 times 2 and multiply by 4. Take that 3 out, and everything eventually becomes 1/2 0 to 1. Hopefully sigma squared minus sigma to the power 4 over 3 times k squared over 4m squared minus 1 minus sigma squared times k squared. That's the form of I that we want to use. Now, as I mentioned, the integration over k, we are going to substitute this here and integrate over k. So, delta V of R will be some prefactors d3k over 2 pi cubed 1 over k squared times k squared over 4m squared minus this is plus, by the way, plus 1 minus sigma squared times k squared. This cancels that. So the integral over k, there is also an expression of I k that R. So you have an integral of the form d3k over 2 pi cubed exponential of I k dot R over k squared plus mu squared. The mu squared is divided by 1 minus sigma squared is 4m squared divided by 1 minus sigma squared. Okay? And you know how to evaluate this integral. Does anybody know its answer?
You will get an exponential over R.
This is what Yukawa did. Yukawa basically evaluated this integral and got Nobel Prize for it. So, it's the Yukawa potential. And the Nobel Prize he didn't get for evaluation of an integral, he got for the idea of introducing polymeson as the particle which transmits interaction between nuclei. Okay? But this is the Yukawa force. That's precisely the Yukawa force. So if the particle is massive, it's exponentially damping. If mu is 0, then this will be 1 and you get the Coulomb force, which has infinite range. Okay? So that's the form that you get, and we are going to substitute it with one further change of variable. Therefore, I'm going to write the final form. But I will not go through the steps of this extra change of variable. I want just to show you. Here, of course, you will also have the d sigma integral from 0 to 1, other factors, etc. So you can change once more from sigma to another variable and bring it to the form which is usually known as the Ullin potential. And in this form, it was calculated before the development of covariant perturbation theory in QD. It was calculated in 1935, I think, or 1930 something. So there is another change of variable. Change sigma to zeta, which is 1 minus sigma squared the reason we are doing this change of variable is that, as I mentioned here, this mu squared, in order to bring this to that form, to that canonical form, you have to divide by 1 minus sigma squared. Therefore, mu squared is 4m squared divided by 1 minus sigma squared. What you have here is mu. That's the square root of this. That's 2m divided by square root of 1 minus sigma squared, standing on the exponent. That's not very nice. So if you make that change of variable in the exponent, you will have instead 2m times zeta times r. Okay? It will look neater, but then the integrand will look a little bit complicated. So putting everything together, we write the complete potential as the sum of the Coulomb part, a big bracket 1 plus e squared divided by 12 pi squared 1 to infinity. This integration, if sigma is 0, that's the lower one, zeta becomes 1. If sigma is 1, this becomes 0 to power minus, it becomes infinite. But then the integrand here looks quite complicated. The exponent looks nicer, the integrand looks complicated. Or zeta. That's our, this is called Uhling potential. Okay. Now from this form, you can extract the behavior of this extra term for small and large values of r. How it behaves when r becomes large and how it behaves when r becomes small. I will quote the result and leave it to you to drive it. This will be an exercise in. But before doing that, let me make another step. The other step is that we are going to write this in a slightly different form. First of all, the potential energy is obtained, or the interaction energy of the source with this field is E times V, and I will take Q to be some pure number, positive or negative, times E. If, for example, is the charge of the nucleus of an atom, this will be just Z, the atomic number, and therefore EV becomes Q bar divided by pi times 1 over r, and the rest I'm going to call an effective charge r. So obviously, if I write q like this and multiply V by E, there will be an E squared. So I can tell you then what's the effective charge. This E effective, which depends on the distance, is the E squared times 1 plus E squared divided by 12 pi squared 1 to infinity d zeta divided by zeta to the power 4 times the rest. We have written it deliberately as a Coulomb potential, but with a charge as a Coulomb energy with a charge which is different from just a constant E squared. If this term was not here, it would be just E squared, it would be this standard thing. Okay? There will be nothing strange about it. But with that extra term, it deviates from the standard thing. How much it deviates? It deviates is 1 plus this, it deviates as much as this object is. And obviously that deviation from the standard Coulomb potential depends on distance. R is here. R is sitting here. So we should find out how much it deviates when you go far from the charge and how much it deviates when you go very close to it. That means we should study this effective charge in two limits of large and smaller. But what's large and smaller? Who tells you what's large and what's small? Who tells you that? The mass of the electron. There is a length scale which is the Compton wavelength of the electron. So you can compare it with the mass of the electron. Therefore, there are two limits. One is R, much bigger than 1 over m. And the exercise is for you to show that in that limit you can approximate the effective charge by 1 plus alpha divided by 4 square root of pi times exponential of minus 2 mr over mr to the power 3/2. As you expect, if you are in a distance far bigger than the Compton wavelengths of the electron, there is a correction which is exponentially decaying. Okay? The other limit is R much smaller than the Compton wavelengths. This is obviously the place where you expect something interesting to happen. And it was so interesting that from it, Landau decided that not only QED, but all the field theories are dead. And I'll tell you in a minute why he decided that. In that limit, it becomes 1 plus 2 alpha over 3 pi. You have to do that integral up, you have to evaluate this integral approximately in that limit to obtain this result. Plus some constant. This constant is not important, but I'm going to write it. It just comes from the evaluation of the integral. Obviously, when mr is much smaller than 1, or r is much smaller than the Compton wavelengths of the electron, this term becomes large. Okay? So it doesn't matter what you have written here. And there will be a distance at which the correction will overtake the leading term. Then you will understand that the approximation doesn't work. Okay? So that's not a good thing. When will that happen? It will happen when this term becomes comparable to that term. That means when 2 alpha over 3 pi log of 1 over mr becomes comparable to 1. And from there, you can find out where the breakdown, that we call RB for the breaking of approximation, will happen. So it will happen
To minus 1.
I think
Comparable to minus 1.
Yeah, minus 1. Because of the log is
Yeah.
no, it's okay. This is comparable to that. So this is a minus. There is a 1 over mr, so that is log of minus of log of mr. Therefore, mrb becomes exponential of minus 3 pi over alpha. 2 alpha. Okay, so it is much smaller than the Compton wavelengths of the electron, as it should be, because the approximation was in that range. Rb equals to 1 over m times this very small number. This is a very small number. If you take alpha to be 1 over 137, That's in the denominator, so it is exponential of minus 3 times pi times 137 divided by 2. And that's a very large number. Therefore, it's a very small number. That means you are a very short distance. Now, yeah, we have some 5 minutes. So this is called a Landau pole. You don't see a pole here, but you'll see a pole in a minute. Any questions? QCD was a big discovery because it behaves exactly the opposite way. When you go to short distance, the effective coupling becomes smaller rather than diverging. If we had done the calculation for phi cubed, we didn't calculate the coupling constant for phi cubed. Phi cubed behaves like QCD. But phi to the 4 behaves like QD, and QD behaves in this way. That means they indicate Landau pole at high energies or short distances. And usually the way that this is expressed, people do not write in terms of distance. They obtain that result from studying the renormalization group. And that also you can obtain from these arguments. So let's see how we get the QED beta function from here. You remember that we introduced something called the beta function when we were doing the renormalization of the pi to 4 coupling. The way we do that, we go back to the effective coupling. In fact, this is the equation we want to take. And ask ourselves the question, how fast is this coupling growing? And to answer that question, of course, we look at this differential. We look at the derivative with respect to r. So if I evaluate the effective square divided by dr, r appears only here. The rest, when you take the derivatives, gives you 0. And it's easy calculation to show that it is just minus e to the 4 divided by 6 pi squared. Now, to the order that we are studying, I can replace that e to the 4 by e effective to the power 4, because the difference between e squared and the effective squared is already of the order of 4. This alpha has another e squared in it. Okay? So I'm going to write this as minus e effective to the power 4 divided by 6 pi squared. Usually this equation is written in terms of the energy rather than distance. So if you change a variable from r to mu, which is 1 over r, and define beta, which is dE effective by d mu, it's logarithmic derivative of d effective by d mu.
Isn't this missing something? Isn't that the units are not right?
What's that, right?
There's like a dependence on leg on one side.
Oh, yes.
1 over r.
Yeah, there should be, no, also in the notes, yes. There should be 1 over r.
Okay.
Thank you. You can actually use these equations. See, since you have the derivative of e with respect to r, therefore you have the derivative of e with respect to mu, and calculate this function. And this will turn out to be the famous result, e effective cubed divided by 12 pi squared, which is positive. It shows that as we increase the energy, that means when you go to short distances, e is increasing. Now that's one thing. This is the way that this whole discussion is usually framed. But another thing that you can do is a bold step from here. The bold step is that just consider this as a differential equation and solve it. The differential equation is I'm going to solve in terms of mu. Since we are running out of time, I'm just going to write the solution. You can read the result in the steps in the notes. It's an easy thing. You know the derivative of a function, and you can solve it. You see, we obtained that equation from a one-loop calculation, and we retain terms of the order of e squared here. But the solution, obviously, as you will see, will have all powers of e. Then we have to understand what's the meaning of it. But let me write just the final result. You can rewrite everything in terms of an alpha effective as a function of mu. Alpha effective is defined like E effective by E squared, like alpha, ordinary alpha by E squared divided by 4 pi. It's a first differential equation, so it will have an integration constant, which is the value of alpha effective at some fixed mu, 1 minus 2 alpha effective mu 0 divided by 3 pi times logarithm of mu over mu 0. So this is what's called the running coupling constant. The coupling constant runs with energy or with distance. Okay? And you see that as you increase the energy, as mu becomes bigger than this reference mass mu 0, for example, you can take the mu 0 to be just electron mass. In that case, this would be 1 over 137 of the electron mass. You see that as mu becomes much larger than mu 0, this function increases, and the denominator 1 minus that function decreases. And therefore, the whole fraction increases. Alpha increases. When you go to higher energies, alpha becomes stronger and stronger. This is again the same phenomenon that we saw here. And the place where it will break down can be worked out again from there. That means when this becomes an order of 1, you will get the same result as here, except that now you will have it in terms of energy. Okay? And it will happen at an energy of mu 0. It's just the rewriting of that expression. Despite the fact that we have a logarithm here, we have a denominator which has infinite powers of the coupling. If we write this alpha, so now it comes with positive power. It's very large energy, this energy, corresponding to a very short distance. We will see later that this solving a differential equation like this, plugging in it the one loop result, in fact, is summing for you infinite number of graphs. This is one of the achievements of the normalization group, that it gives you more information than you have put inside. Okay, so I guess we can stop at this point and continue next time.